Welcome to this explainer. If you've ever sat in a cold lecture hall while a professor just frantically filled a massive blackboard with differential equations, you've probably felt that familiar knot of anxiety forming in your stomach. Well, today we're going to completely let all of that go. We are taking a calm, super supportive look at how electrical circuits actually adjust to change over time. We'll be exploring the time domain analysis of first-order RL and RC circuits, but absolutely without any of the usual pressure. Instead, we're going to focus on the beautiful, natural reality of what the math is actually trying to tell us. So take a deep breath and let's explore this together. I want you to picture something for a second. Think about some everyday, really sudden changes. Like, imagine slamming the brakes on a fast-moving car. The car doesn't just instantly freeze in place, right? No way. It skids, it slows down, it literally takes time to halt. Or think about pouring yourself a piping hot cup of coffee. It doesn't magically become room temperature the second it hits the mug. You actually have to wait for it to slowly cool down. Notice how these physical events always require a period of adjustment. The universe simply doesn't do instant. There is always a transition. Okay, so let's bring that exact same real-world analogy right over to our electrical circuits. Just like a car's physical momentum resists a sudden change in speed, certain elements inside a circuit resist sudden changes in electrical flow. When you flip a switch and close a circuit, the electricity doesn't just instantly and perfectly arrive at its final state. The circuit itself actually has a mandatory adjustment period. The energy literally needs a moment to sort itself out, to either build up or to fade away. Section 1. Meet the energy stores. To really understand why this mandatory adjustment happens, let's meet the main characters of our story. These are the specific components that make this adjustment period an absolute necessity. First up, the capacitor in an RC circuit. You can think of a capacitor exactly like a giant water tank. It stores energy in an electric field, gathering up charge the same way water slowly fills a reservoir. It takes time to fill up, and it takes time to drain. On the flip side, we have the inductor in an RL circuit, which stores energy in a magnetic field. Imagine the inductor like a really heavy spinning metal flywheel. If you try to stop that heavy wheel instantly, it's going to fight you hard. It desperately wants to keep the current flowing. Both of these components essentially act as a memory of what the circuit was doing just a fraction of a second ago. So let's break down exactly how these components react right after a switch is closed. In physics, we call this precise moment time equals 0 plus. In their own unique ways, they inherently oppose sudden shifts. The capacitor outright refuses to let voltage change in 0 seconds. It acts like an open circuit. The inductor, meanwhile, utterly refuses to let the current change instantly, acting like a short circuit. Because they're physically holding on to energy, either as a gathered electrical charge or a magnetic field, it takes a literal physical duration of time to either gather new energy or dissipate what they already have. All that complex math you see in textbooks, it's really just a reflection of this very physical, stubborn reality. Section 2. The circuit's speed limit. So, if circuits need time to transition, how do we actually know how long it's going to take? Well, we use a very special metric. If we completely strip away the noise of the equations, we're left with this beautifully simple concept, the time constant, represented by the Greek letter tau. I actually love to think of tau not just as some dry formula, but as the inherent personality, or the natural speed limit of a specific circuit. For a circuit with an inductor and a resistor, tau is just the inductance divided by the resistance, L over R. And for a circuit with a capacitor, tau is simply the resistance multiplied by the capacitance, R times C. This one single number dictates the absolute speed limit of the circuit. It tells you exactly how fast all that initial chaos is going to settle down. Now, here is where things get really fascinating. There is a magic number, 63.2%. When a circuit is adjusting to a brand new energy source, say you flip a switch to charge it up, the rising current or voltage doesn't just climb up in a straight linear line. It curves. And amazingly, it reaches exactly 63.2% of its final steady destination in the time span of one single time constant, 1 tau. It's literally a universal law for these types of linear circuits. Conversely, if we look at a source-free circuit, meaning the power is totally cut, and the circuit is just naturally draining away its stored energy, the response drops down to exactly 36.8% of its starting value in that exact same span of one time constant. So whether it's filling all the way up or emptying completely out, the time constant perfectly dictates the rhythm of the decay. Section 3, a story in 2 parts. Okay, if you're reading through a standard engineering textbook, you are going to hit a massive wall of dense mathematics right about here. You'll see the phrase non-homogeneous linear differential equations used to describe step voltage responses. Honestly, that sounds incredibly intimidating. But I want to reassure you right now, all that heavy mathematical jargon merely translates to a story with two very simple components. It just describes a journey that is currently happening and the final destination where that journey will end. That's really all a complete response is. Let's compare these two parts of our story. First, we have the forced response, which is the steady state the circuit is basically being pushed toward by an external source, like a battery continuously applying voltage. That is our final destination. On the other side, we have the natural response. This is the temporary transient state. It's the circuit's internal stored energy naturally fading away over time, which, as we know, is governed by our time constant, tau. It's basically the fading echoes of the past. When you boil everything down, you get this brilliantly simple equation. The complete current, I, equals IC plus IP, the complementary solution plus the particular solution. In completely plain terms, the complete electrical behavior of the circuit is literally just the addition of these two simple parts. You take the transient, natural response that's fading out, and you add it to the steady, forced state that's taking over. You're quite literally just adding the journey to the destination. Section 4, Finding Your Steady State. Finally, let's gently guide our circuit into the very last stage of its journey. This is the point where the adjustment period finishes up, the chaos totally ends, and things settle into a permanent, quiet groove. When you map out the curve of an RL circuit, you can actually see the transient current steadily decaying over time. As the time constant stretches from 1 tau to 2 tau to 3, the natural response completely fades toward zero. The initial shock of the switch flipping is forgotten. The stored energy is smoothly dissipated or fully integrated, and the circuit finally finds its peace. Now, when we say time equals infinity in circuit analysis, we don't literally mean forever. We just mean, mathematically speaking, the adjustment is completely over. At this steady state, the physical reality of the circuit simplifies beautifully. The inductor, which is now completely settled with its magnetic field, stops fighting and just lets DC current flow freely. It acts just like a plain piece of wire, a short circuit. And the capacitor, fully charged to the brim like a totally full water tank, it stops accepting any more charge, acting completely like an open circuit. The transition is absolutely finished. I want to leave you with this thought. These first-order circuits show us, with pure mathematics, that absolutely nothing can jump from one state to another without a period of transition. It physically requires time to dissipate the old energy and adjust to the new reality. And you know, like these circuits, you too are allowed to take time to adjust to new and difficult things. You have your own time constant. So the next time you feel totally overwhelmed by a sudden change in your life, or even just by a page full of differential equations, remember the humble capacitor and the inductor. They don't panic, they just follow their natural curve toward equilibrium. Thank you so much for joining me for this explainer, and I'll catch you in the next one.